All right, hello. My name is Tim Wood. I'm from the George Washington University, and I'm going to be presenting about OpenNetVM, which is a high-performance network function virtualization platform that we've been building in my research group. And this is really a collaboration with some other people, so some other faculty at University of California, Riverside, as well as IBM Research. So a lot of different students and other researchers have helped with this project. So this is definitely thanks to them as well. So first, let me introduce myself. As I said, I'm Tim Wood. I'm a professor at George Washington University. I got my PhD from University of Massachusetts Amherst in 2011, so I haven't been at GW too long. And I do research in the area of virtualization and operating systems, especially looking at how do you manage big cloud computing data centers. But more recently, I've been very interested in software-based networks, and that includes both SDN and NFV, which I'll describe in a moment. And just so you know, I work at GW, which is in Washington, D.C., so we're about 4 or 5 blocks away from where the president lives in our country. We're a pretty large university, but we have a small computer science department. It's about 15 faculty, 80 PhD students, 300 masters, and 150 undergraduate students. So if you're interested in any of these things, you can go to my website and learn a lot more about both my research as well as our department and university. So I'm going to be talking about networks today and how they interact with system software. And this is becoming a very interesting area because networks are really changing. It used to be that networks were quite simple. Right? We would just have a few computers connected together with some kind of switch or hub. But now networks are very complicated. We have very complex data center networks with very hierarchical structures. And we also have wide area networks where many different ISPs are coming together to build the overall internet. And there's a lot of complexity at the edges of these networks about how they interact with each other. So recently there have been 2 new technologies that are changing how we build networks and how we control them. And those are software-defined networking, or SDN, and network function virtualization, or NFV. And these are changing both the hardware and the control plane that runs the network. So software-defined networking is focusing on the control plane of the network. By that I mean it looks at how you route packets through the network. So you control each flow, which path it should take. And in the past, every router would talk with adjacent routers to figure out how routing should be done. But now with SDN, we have a centralized controller which will contain the rules for how packets should be routed in the network. So now a switch or router, when they need help deciding how to route a packet, they will do a lookup to the SDN controller by sending the first packet of the flow to the controller, and then the controller can give you back a rule. So the SDN controller could be inside a data center. It might just be managing the network within that data center, or it could be used in a wide area network, and it's helping decide how you route packets between routers in the wide area. And basically it takes in a packet, it looks at the header information of that packet, and then it has some rule that says this is where this packet should go next. And being able to do this in a piece of software, in the SDN software, gives us a lot more control over how packets are routed through the network. The other technology is network function virtualization, or NFV, and this is focused on the data plane. So by that I mean that it looks at how we process individual packets, not just how they route through the network. So there's some examples of what I mean by a network function here. So a router or a switch are very simple network functions. They take in a packet and then they send that packet out a different port on the network. Other network functions can be much more complicated. So a firewall might have a list of rules that it has to analyze for each packet. Or an intrusion detection system, that's IDS, that's going to be even more complicated. It will have to analyze each of the packets, maybe reconstruct a flow based on several packets, and do some kind of security monitoring. So all of these are examples of network functions, and in the past we had to run these as hardware. We would have what's called a hardware middle box, which was a specialized device that would perform the network function on each packet. With network function virtualization, instead of having these hardware devices, we can now run these things as software, and we can run them inside virtual machines. So this has a lot of benefits compared to using hardware. This is much more flexible. It also isolates the functionality between these different network functions, but it has some drawbacks, right? Running this in software is generally going to be slower than hardware. So one of the challenges that this project is looking at is how can we make these network functions run as fast as if they were in special hardware. And that's very difficult to do. So this area of software-based networking is the combination of SDN and NFV. And I think it's a very interesting area because now networking is more than just transport. It isn't just moving data from one computer to another computer. Now the network can be providing services as that data is being moved. So it might provide security, it might provide quality of service. You can do things like transcode videos as they go through the network. So this is very interesting that the network itself can be very powerful and can provide services to the data moving through it. The problem is that most of the systems level software for network software isn't very good. So operating systems are not designed today to be able to handle the very high rates of packets that you need to be able to do this. So operating systems like Linux, they need to be improved to be able to support these types of network function virtualization. We have to manage our resources much more carefully, and we really have to take advantage of multi-core systems to get parallelism and help minimize latency. And of course that's very important because we can't add overhead to all of these packets that are going through the network. If we slow down the network, then people won't use this. So this is an interesting opportunity to redesign how we think about the network and what it's able to do. And because of that, it's really a convergence of many different research areas. My perspective is from the operating systems research area, but I work with people that focus on networking or focus on security or big data stream processing, and all of us can work together to see how we need to redesign the network to be able to support these interesting services. Okay, so today I'm going to talk a little bit about how packets get processed in the Linux operating system and how we've designed our OpenNetVM platform to try to improve this. So this is a platform for doing very efficient packet processing in virtual machines or in lightweight containers. And we've really optimized it to be able to reach speeds of around 70 gigabits per second. So remember, the comparison point is to do all of this in hardware. So if we run these network functions in hardware, they're very fast, but they're also very expensive and they're not flexible. We can't dynamically change what software is running because the hardware can only do one thing. And here's just an example of a fairly cheap router that you can buy. So it costs 33,000 US dollars, and that's pretty expensive. And certainly they can be more expensive than this. So we would much prefer to be able to do this inside of software, especially if we could do it at the same speed and if we could have more flexibility in the software than we would in hardware. The problem is that software is complicated. So I think this is a great image. If you haven't seen this before, this is the Linux kernel map. And if you search for that, you can find a web page that will show this to you, and you can see sort of the overall structure of the Linux operating system, and you can click on the different components and it will take you directly to the code related to those different pieces of the system. And on the right side, you can see the networking stack in kind of a light blue color. And you can see that there's quite a bit of complexity in how the operating system handles network packets from when it first arrives on the network interface card and then goes all the way up to eventually reach a socket and a user level application. So here we just zoom in on the networking portion here. And again, you can see these many different layers, right? A packet comes in, it goes to a network device. That has a driver, which will then talk with the operating system to manage how memory is allocated for the packets being received on the network device. When a packet does arrive, it has to go through a protocol layer because the operating system will handle TCP protocol or UDP protocol and so on. And eventually it goes to the socket layer in the operating system, and then finally the packet data can be copied from the kernel space into the user space where your application is running. So this is a lot of complexity, and it turns out that for these NFV middle boxes, we don't need all of this complexity. And this is because most of these network functions, like a firewall or a switch, they just need to look at the individual packets. So they don't need the operating system to provide a TCP layer or a UDP layer or to provide the abstraction of a socket. With NFV, we just want to get direct access to the packet data and be able to work with it as quickly as possible. So a big part of our project is trying to eliminate these software layers so that we don't have to pay the cost inside the operating system for each packet. So as I said, with traditional networking in Linux, the packet will arrive at the NIC and it will use DMA to copy the data of that packet into a kernel buffer. Then you have to send an interrupt to notify the operating system that this packet has arrived. And then it will go through all of the layers that we saw on the previous slide inside the kernel, and eventually the data from this packet will be copied from kernel space to user space. And similarly, if you're going the other direction, if you have a user application that's trying to send out a packet, you'll have to use a system call to transmit the packet from user space to the kernel space, copy the data, and so on. All right, so there's a lot of packet copying going on here. There's also these interrupts that need to be issued. So if you're sending or receiving packets at a very high rate, these overheads can become very, very high. So for example, if you want to be able to process packets at a 10 gigabit per second rate, and if these are the smallest possible packets, which means they're 64-byte packets, then you need to be able to handle about 14 million interrupts every single second if you don't do any batching or anything like that. So clearly that can become very inefficient. You might spend more time handling the interrupts than you actually spend doing any kind of processing. So we need to think about other ways to be able to receive packets from the network card and get them to a user application which will be able to process them. So to do this, we're making use of a software framework called Intel Data Plane Development Kit, or DPDK. And what this does is it uses some recent advances in the network card technology to make it so that the packet data can directly go from the network card to a user space buffer. So we have a special driver for the network card, and it will DMA the data bypassing the kernel and going straight into user space. Then instead of having interrupts, we will have this user space framework use polling to find out when packets arrive. And of course there's a trade-off here. If you use interrupts, it can be more efficient if there's a very low rate of packets arriving. But if there's a very high rate of packets arriving, then polling will be much better. And since we expect a very high rate of packets, we know that polling is going to be better in this case. So that's why we can poll and constantly be checking for when new packets have arrived. And finally, because we're not using the operating system to interface with the networking card, if our user application wants to send a packet back out of the network card, it just needs to issue a regular function call. It doesn't have to use a system call anymore because our user space data is able to directly work with the driver to send the packet back out of the network card. So this is something that's provided by DPDK. It's actually a very nice software framework that I would encourage you to look at. It's very unusual because it's an open source project that has very good documentation. So that's quite rare to find good documents, but this is one of the few projects that does have that. So it's a good one to look at and learn from. The problem is that even with DPDK, there's still some issues to be able to build a network function virtualization platform. And that's because we don't have support with DPDK for using virtualization very easily. So we would like to have a virtualization layer between the hardware and your different user applications, because we would like to be able to run many different network functions, each inside of some kind of virtual machine or container. And that's what our OpenNetVM project is trying to do. So here's the overall architecture of OpenNetVM. You can see that from the picture on the right, that at the bottom we still have our network card. We're using Linux and DPDK, but for the most part we can bypass Linux and have packet data go directly from the network card into a shared memory region that's inside user space. So the key idea in OpenNetVM is to get packets into a shared memory region managed by what we call the NF manager, and then to be able to share that memory with each of our different network functions which are running inside either a container or a virtual machine. In our current software, we're using Docker containers to run each of the network functions, and that allows us to very easily start up new network functions and have them share this memory where all of the packets will be located. So OpenNetVM has a bunch of different features that you can see here. It's NUMA aware, so by that it means that the system is aware that the server you're running this on may have multiple CPU sockets, and it will try to be smart about where it sends packet data and which cores it uses to process those packets. The key idea is zero copy, so we don't have to copy the packet data multiple times because it just lands in shared memory and then it can be shared with each of the NFs. We're not using interrupts. Instead, we can use the DPDK poll mode driver to get the data very quickly. And it's very scalable. So we have these receive and transmit threads, RX and TX threads, that are inside the manager that help move the packets between the different network functions. And we can easily scale those up and down as needed. And finally, it's an SDN-enabled platform. So this NF manager, it can communicate with a separate SDN controller to find out rules about how a flow should be processed. So it might get a rule that says when a packet arrives from this IP address, it needs to go to the firewall, then it should be processed by an intrusion detection system, and then it should go through some kind of video transcoding network function. So the SDN controller can provide those rules, and the NF manager will enforce them as the packets move through the system. So this is zooming in to see a few more of the components that make up OpenNetVM. I think I've described most of these. So again, your NFs are running inside containers. The manager is keeping track of these containers, and you have RX threads that receive packets, TX threads that copy packet pointers, but not actually the full packet to move the data between these different network functions. And we need to be very careful to avoid things like locks, which can be very slow, and instead use shared memory and ring buffers to safely move the packets between these network functions instead of having to wait for locking to be done. So the main way that OpenNetVM is improving performance is by getting rid of packet copies. And this is especially important when you have a service chain of network functions. So as I said, you might have several different network functions like the firewall, the intrusion detection system, and the video transcoder that all need to process these packets. And in existing systems, this can be very inefficient. In this diagram here, each of these different arrows represents a packet being copied in some way. So first the packet arrives and is DMA'd into the host OS or the hypervisor, but then you might have to copy that packet to take it from the hypervisor into the kernel of a virtual machine. And then you have to copy that packet again to go from the kernel to the network function. And if you go from the network function back to the kernel, it's another copy, from the kernel to the host, another copy, and so on. So if a packet has to go through 3 different virtual machines, and you're doing this with traditional software techniques, you're going to have 12 DMAs to go to, or sorry, 2 DMAs to go from the NIC to the memory of the host, and then 12 copies to move between the host and the kernel and the network function. So that can be very expensive, and that's why traditional software approaches don't work for these types of NFV systems. With NetVM, we do 0 copy I/O. So we just need to DMA this packet once into the NetVM shared memory area. And then in my figure on the right, these dashed arrows that I have, those aren't real packet copies. We don't have to copy all of the packet data. Instead, we just have to give the network function a pointer to where that data is located. So that's much more efficient than copying the entire packet back and forth. So in the NetVM system, we still have to do the 2 DMAs, right? You need to get the packet into memory, but because we can DMA the packet directly into shared memory, where the network functions can reach it, we never have to copy the packet again as it's moving between our different functions. So this makes NetVM much more efficient when you have these long chains of network functions compared to other systems. So here's some performance results that show how this improves things. So we're using Docker containers to run our network functions, and here we're adjusting the length of a chain. So whether you just have a single NF all the way up to having 6 NFs together in a chain. And we compare in the red bar, just running OpenNetVM, but there we're actually not using the containers at all. We're just running individual processes for each of these network functions. And the green bar shows what happens if we put the network functions inside Docker containers. And you see that there's essentially no difference between the two. So this is the benefit of using Docker containers to run our network functions, is they're adding very, very little extra overhead. There's almost no performance difference at all between running directly in the host or running inside a Docker container. Here we're comparing against ClickOS, which is another research platform that you can read about in some papers. In their platform, they use Xen virtual machines to run their different network functions. And they're designed to be very lightweight, small network functions. So they have some benefits that we don't have. They can very quickly start up these functions, and they can run a very large number of them. But you can see that their performance is not as good as ours, and the performance drops off as you extend the length of the chain. And we weren't even able to run a chain length of 6 for ClickOS because it was just too slow. Whereas our system continues to scale as long as you have more CPU cores to give to each of the new network functions that you add. Here you can see how NetVM does compared to standard Linux, and Linux is pretty terrible. You can barely see the line for Linux at the bottom left. In this graph, the x-axis is the input rate, so the rate that packets are arriving in thousands of packets per second, and the y-axis is the forwarding rate, so that's how quickly you're sending packets out of the system. So we would like those to be equal. And that's why the NetVM line is basically a straight diagonal. The faster packets come in, the faster we can send them out. Whereas these other systems just aren't able to keep up with the speed of packet processing that you need. And finally, I think this is my last experiment that shows the scalability of this system when you're using some more realistic traffic. So here we're sending web traffic, or HTTP packets, through our OpenNetVM system. And you can see that if we have a single receive thread, and we have one transmit thread, and we're running one NF, we can get about 50 gigabits per second of traffic through the system. So we only need 3 CPU cores, and we can hit a 50 gigabit rate, which is quite fast. After that, the receive thread is actually the bottleneck. So if we add a second RX thread or a second TX thread, we can boost the performance up to about 68 gigabits per second. At that point, I think it's actually our network card, which is the bottleneck. We haven't really been able to get the full rate out of the network cards. But that's quite a large amount of traffic that we're processing. So you could imagine that this could be used for some kind of software router, even in a very high-speed network. And the final bar on the right that says 5 NFs, here we have a more complex chain of 5 network functions that we need to send packets through. And this is a more complicated network function example, so it only hits 38 gigabits per second, but that still is quite a fast speed. So realistic traffic could be analyzed by 5 different network functions, and you still would be able to do this on a high-speed network pretty efficiently. Okay, so the final point I want to make about NetVM is that when combined with software-defined networking, it can give you very high flexibility. The way we do this is that we have the idea of a service graph. And a service graph is going to be a list of NFs that a flow of packets may need to go through. So on the right here, I have 2 different service graphs, the red graph and the blue graph. And you can see that each of the circles is a different network function that might need to process some packets. So the red graph is a video transcoding set of network functions. So packets come in, they go through a video detector, you figure out if this is a video flow or a regular flow. You may have to adjust the quality of the video, do transcoding or caching, or some kind of traffic shaping. And each of those are going to be different network functions that could be running on OpenNetVM. And the blue flow is a security service chain. So we have, again, about 5 different network functions that would be analyzing your traffic and determining if there's some kind of security problem in your network. So with OpenNetVM, we can run all of these different network functions across several different machines, and then we can use an SDN controller to provide the set of rules that guide the packets through the service graph that the SDN controller wants that packet to see. So the SDN controller will determine for each flow whether it should go through the red service graph or the blue service graph. And what's most interesting here is that we can get these general rules from the SDN controller. It provides us this high-level service graph, but then each of the network functions, they can still make decisions about how the packets are processed. So they might just follow the default rule provided by the SDN controller, or they can slightly change the path that the packets will go through. And this is important because it's really these network functions that are able to look inside the packet data and decide how it should be sent. The SDN controller doesn't know all of that information. So the SDN controller can only provide you a high-level set of possible rules, but then we allow the network functions to choose the precise rules that will process each packet. So this lets us split up the control between the SDN controller and the individual network functions. And that gives us very high flexibility, but also very high performance, because as we've seen in the previous slides, the network functions can process packets very, very quickly. All right, so to summarize what we've been doing is we've built the NetVM or OpenNetVM platform, and it's a very high performance software data plane And it also includes components to talk with an SDN controller so that you can combine a control plane with this high-performance data plane. NetVM mainly focuses on giving you very high-speed packet delivery to these network functions and through chains of network functions, and it achieves this by using memory sharing between each of the different NFs. And the goal is to build a very easy-to-use platform for building complex network services that can do packet processing in a very efficient way. So we have released this code as open source. You can check out our website to find the code. We also have a few papers about the project, which you can find at that website as well, to really hear about the technical details behind this system. So I hope you've learned something from our talk, and thank you very much for listening.